And here's how they did it. Okay. First off, it asks find the distance between ships A and B when x is 4 and y is 3. And I gave you the hint that this was not a calculus question. This is a Pythagorean theorem question. It's saying, here are my two legs, what's the hypotenuse? So c squared equals a squared plus b squared, and it's a 3, 4, 5 triangle. One of the easiest points I've ever seen on the AP test. They asked you to do Pythagorean theorem, and they gave you a point for it. No calculus required. Now, the reason they had you do that is because you're going to need it in the next two parts of the question. So they made sure you had that set up before they moved on and said, find the rate of change of the distance. Well, here comes Pythagorean theorem again. So they used r for the hypotenuse. And what I personally would do here is I'd plug in for all my things aside from dr dt into this equation and solve for dr dt. Either way, you should get -6. My units are kilometers per hour. The biggest thing here is to make sure you put -15 in there for that dx dt. Dx dt there was negative. And notice that my rate of change of the distance is also negative. Let's see what happens to the rate of change of the angle. Like I had said before, we're using tangent. Derivative gets to the quotient rule. Since I know that the hypotenuse now is 5, that means the cosine should be 4 over 5, adjacent over hypotenuse, which means that secant should be 5 over 4. That flipped. So we're going to take that, put that in, and square it right over here for secant squared. So 5 over 4, and then that's going to get divided. So I should get 17 over 5. 85 over 25, which simplifies to 17 over 5. Radians per hour is my unit. My theta there is in radians, and then per hour for my dt. So again, that one was a little bit more complicated. We hadn't done one that used a quotient rule yet. We will do one other one that uses trig and the quotient rule. So let's look at it and do that. Questions on this one before we move on to that? All right, here we go. We did that one. We did this one, right? Yes. All right, here's the next one. Not here, over here. Yes, this is my next one. All right, I will give you a moment here. And I will close this. And see if you can draw this picture. just full disclosure, when I drew this picture, or when I'm about to draw this picture, I'm going to draw the person being to the left of the street light. So the street light is going to be on the right side, the person's going to be on the left side. It will also help you to know what things are constant in that picture that you draw and what things are actually changing. What distances are actually changing. What you should end up with here is two rates. One rate that it gives you and one rate that you're trying to find. And everything else in the diagram should stay constant. All right, here we go. First off, there's my street light. Okay, and it tells us that this street light is 16 feet above the ground. Is that a fixed distance that always stays the same no matter what, or is it a distance that is going to change? And then I'm going to have to keep in, all right, that's a constant. No matter what else happens in the problem, the height of my street lamp is going to be the same. All right. Now, we are going to draw the ground. There's the ground. All right. Next, I am going to draw a person. There's my person. All right. This distance is given in the problem. What is it? Okay. Do we want to use a variable that is changing, or do we say that it's fixed? It's changing. So I'm actually going to use a variable there. And it went in black anyway. Not what I wanted. X. There we go. And I'm going to go ahead and complete out some triangles. This is the light that the street light is casting down onto the person. And passed them onto the ground. This is the ground, remember? That's the ground. That's my person. All right. Huh? Oh, yeah, it's right there. That's where the light is. All right. I'm going to, now, be kind enough to point out the next place, which is where it's asking about the length of the shadow. So where's the shadow? Starting where? On the ground, intersecting with the person. And then I go, because the light is casting down, so I go this way. Is that a rate that we are trying to find in a variable, or is it a fixed distance? It's going to be a variable. All right. One more distance is given, which is staying the same. That's the height of my person. All right, here's the idea. Here's how we're going to solve this. Is that I have two triangles happening. I've got this triangle right here, which is my my person with the shadow, and then I have the bigger triangle here, which is the street light down to the ground. And these two triangles, since these create right angle here and common angle here with the reflexive property, are similar triangles. Angle-angle similarity. There's some geometry for you. So these two triangles are similar. So I can set the matching sides up in a proportion with each other. So on the left side, I'm going to have the heights. Equals. And then on the right side, I'm going to have the distances along the ground. My distance along the ground in the blue triangle is what? S. My distance along the ground in the green triangle is going to be S plus X. All right. Now, you can go from here and solve for what we're trying to find. But I'm not going to do that because that would be too hard. Or that would be harder than it needs to be. So what I'm going to do instead is I'm going to cross multiply here and get rid of some fractions. So when I do that, I wind up with 6 times S plus X. I'm basically like multiplying both sides to get rid of the fraction. Equals 16S. Yeah? Follow that so far? That's just basic solving proportions stuff. So now I'm going to distribute. Yes? And now let's get everything on the same side. Okay, and I'll stop there. Much easier than to take the derivative of than this thing. This big complicated quotient rule. This, we know what the derivative of 6x is. So let's do that. Derivative of 6x is 6 dx dt. Derivative of 10s is 10 ds dt. Nice and easy. The related rates part of the problem became very, very simple. The complicated part was actually drawing the diagram and getting the geometry set up on this problem. We're trying to find ds dt. Which means we must have dx dt. Oh, here it is. Is that positive or negative? Because we are walking towards the light. So since we are walking in the direction of the light, x is getting smaller. So dx dt was negative 5 feet per second. So I'm going to plug negative 5 in for dx dt. Notice I didn't need s or x in this particular equation. So that's going to be 6 times dx dt was a negative 5 equals 10 ds dt. This is 30, so divided by 10 ds dt. And again, hopefully that makes sense. You might first look at it and say, if this is getting shorter, shouldn't this get longer? But remember, I'm going closer to my light source. So as I get closer to my light source, my shadow should get shorter. And if I were all the way up against here, then the shadow would be barely as long, versus if I'm all the way over here, my shadow is really long. Okay? Questions on that? All right. This next one. I'm going to give you a couple setup parts for it, and then I want you to try it, and I will check you on it tomorrow. So, camera angle. I'm also not going to do all the details. I mostly want you to get to a place where d theta dt is by itself. If you can get to that point, because we are trying to find how fast will the camera angle be changing. So we're trying to find d theta dt on this problem. So I'm going to call this distance x. I'm going to use x because that's a variable, because the race car is moving. The camera is not moving. This distance is fixed. Stays the same. So that's going to be helpful to us, because our derivative should not be a quotient rule, because one of the numbers that we're going to put in the ratio is the 132. So we won't have like an x over y like we just had earlier. One of the numbers is going to be 132, which is going to make the derivative a lot easier to work with. And with that, I'll let you try it.